Today's speaker is John. It's kind of a long way to talk to us, so we should listen very carefully.
Well, thank you, John. That's a nice short introduction. I came the longest way I could also.
No, I came the longest way. Sorry, John.
You did. I think we'll have to debate that later. Is that better?
Is it on?
Okay. It should.
Are we having our side of the platform?
I don't think it actually. What? Well, yesterday it didn't actually come through. It's just for recording. That's right.
Hello. Oh, it's just recording, is it? Okay. Okay. Well, today I'll talk about work I've been doing on cube sphere grids for a while now, 10, 15 years. The model mostly developed is called CCAM, conformal cubic atmospheric model, but got a new formulation which I introduced at the last PDE's meeting and have made a bit more progress. And so the first half I'll talk about how CCAM's formulated and the various tricks you can do on the conformal cubic grid, and then the new model. And for the last 6 months or so I've been making excuses why it's not working as well as CCAM, but I thought I'd better plot it again yesterday, and to my very pleasant surprise it's working better than CCAM. So I'll give up my apologies and see what you think. But I made some changes in the recent run I didn't think were important that actually do assist the whole thing.
So if C was conformal, what's V?
Variable cubic. It's got a secret meaning, of course. The V is really for Vegemite, which is best thing since Vegemite. It's an Australian iconic food.
Vegemite. Oh, that's the British one.
That's debatable too. Okay, so Sidorny back in 1972 came up with the idea of putting a grid on a cube and then projecting it to the centre of the sphere, and that's the original mnemonic grid. He had it just an equally spaced grid on the face of the cube, and that's better than a lat long grid, but it does get a bit crowded near the panel edges because of that projection from further off the sphere. But it's a simple matter to make it equiangular, that distribution of X and Y lines on the cube. And when you do that, you get a very uniform grid. And the VCAM I'll talk about later is on that grid, and a few other, or most other people these days, I think, do use this type of grid when they use a mnemonic cubic grid. However, I started off with this sort of grid, doing advection, semi-Lagrange advection study and so on. And back in '96 at the Andre Robert meeting in Montreal, Jim Purser pointed out, well, there's actually a conformal version of that grid. Why don't you do that? So I used that for 10 or 15 years, and it works well. You alter the distribution of the lines on the cube so that once it's projected onto the sphere, you end up with a family of lines which is everywhere. The lines are everywhere orthogonal, and it's isotropic, delta x equals delta y. And at the panel edges, you don't have any change of direction. Around the vertices, it does curve pretty strongly, but it's still orthogonal, and there are some weak singularities at the vertices, but you have to look very hard to see them. And Stefan has been looking very hard recently to engage in conversations. So the workhorse.
Weaker than the pole and the lat long grid?
I would say so. Jim Purser argues with me on that and says it's really a singularity is a singularity, he reckons. But
can it not be quantified? How the anisotropy changes as you go towards that pole? I mean, we know how it goes towards the pole, in the lat long grid.
So you can you can measure the strength of the singularity by the angular deficiency, and every grid has to add up to 360 degrees of angular deficiency.
Okay.
So each of the singularities here are 90,
Yep.
as opposed. So from a purely mathematical point of view, we would say they're 1/4 as strong as the. I guess no, 45. Sorry, that's the arithmetic, right?
I've been looking at the Laplacian on these grids, and the conformal cube sphere is very bad, much worse than non-Laplacian.
That's what
the
I was
Laplacian.
That's what I was thinking.
I will try to look at that again.
So the finite differencing right near the vertex does get a bit strained, especially the high resolution, but I'm not really running at that limit. Well, I will show some extreme examples which suggest I am running at that limit, but I don't see any problems in practice at the vertices. So the dynamics of CCAM is somewhat like what weather centres use. It's semi-Lagrangian, 2-time level, semi-implicit. Most of the funding we have comes from regional climate modelling, so we need to run in with variable resolution to achieve that. But that's a detail for the purpose of this talk. Something unusual I do have is this reversible staggering, and I'll say more about that, and I'm using it in CCAM formulation and the VCAM formulation. I'm quite attached to that, and so I'll say more about that in a moment. CCAM is a vective form, so you don't have conservation of mass, moisture and other things, so there's no posteriori fixer each time step. I'll say a little bit about that. The physics I won't really go into, but it's GCM style physics with around cumulus scheme and most of the usual things. A few more layers of soil for soil moisture and temperature. So getting on to the reversible interpolation, the arrangement of the grid is like this. We see 3 of the panels here with the local X and Y directions. All variables are stored where the dots are. It's in the centre of the cell, so it's a quadrilateral cell everywhere, even near the vertex it's a quadrilateral cell. But it's nice to have the velocity staggered in an Arakawa C sense for calculating divergence. That avoids separation of solutions and so on, if you do have that. And so what I do is calculate those U's, half a grid point in the X direction, V's half a grid point in the Y direction. But rather than use interpolation, I've come up with a reversible scheme that shifts between them. So you can go backwards and forwards without any diffusion type effects. And I'll show that in a moment. The numbering, the sphere is a bit of fun. You'll see the U's and V's have the same sense here, but when you cross the panel, U's become labelled as V's, which is a bit of fun, but at least the positive U's become the positive V's. So in coding, if you're using indirect addressing, it's the divergence here, you just pick up the north, south, east, west type values automatically picks up whether it's a U or a V. There's no if tests or anything. It's just comes out in the wash.
Can I ask you? I guess I'm curious because, in fact, the velocity at those edges would just be simply a velocity that's normal to the edge, right? So is it really labeled U? I mean, is that what you mean by U and V, or because U and V have meaning in kind of a Cartesian context, but not so much in this context?
Each panel has its own X and Y.
Okay. But really, you just want normal velocities at the edges.
Yeah, on this panel, this is the X and Y, and when they get to the edge of this panel, that's the end of that panel. We're onto another panel.
Is that spherical velocity, orthogonal velocity components for the tensor on what university?
These are just ordinary
So
Or maybe
these
really-
are
ones because the grid's orthogonal.
So
Okay.
okay, so the grids are
You
okay.
don't really, in an indirect sense, you don't really have U and V, right? I mean, you have a local coordinate space when you visit each cell. And so when you've got this thing on the edge that you feel like labeled U, we'll know it's U when you look at it from the left and it's V when you look at it from the right. That doesn't matter.
It's just a normal velocity.
Yeah.
Yeah, it doesn't really matter. But if
So
I'm,
there's no real sense in which those are using this.
if I'm calculating the divergence at this point here, I'd say it's U east minus U west plus V north minus V south. But this V south is automatically
So
picked up
that
as...
V only makes sense in local coordinate space.
Yeah.
I think the point that
yeah.
everybody is making, you just have a velocity with every edge. And it's either not labeled U or V.
It's a normal
Uh-huh.
velocity.
it's a topology issue. And
Yeah.
when you
That's what I
access-
meant.
Yeah.
Yeah, sorry, that's what I meant.
Yeah, all sounds correct. So the way this reversible thing is done, here's a little diagram along a line. So this is the centres of the cells, the whole numbers, m minus 1, m minus 2, minus 1, m plus 1. We've got the unstaggered U's at those points, and we want the staggered values at the crosses. And so introduce a pivot point 3/4 of the way along, and you can write this pivot value here. If you use a 2-point formula, this pivot value is just 3/4 of that one plus 1/4 of that. Or you could write it as 3/4 of the staggered one plus 1/4 of that staggered one. So it's or in a 3-point formula, is those 3 points to equal system, and you can happily go backwards and forwards between the integer values and the half integer values. And being a cubic grid, these are going around the four edges of the it's lines going around the four faces of the cube, either that direction, or the other direction. So it's a cyclic tridiagonal type problem, for which there are solutions, there are routines, but actually have an iterative routine that takes, I think it's 4 iterations, and actually works it's much faster for multiprocessors than trying to go to a normal solver. It's fortunately gives some big MPI type benefits from the iterative solver. So you can look at the dispersion properties on linearized shallow water equations, and following a study of Dave Randall, he did something similar using looking at a vorticity divergence setup and showing how it behaves. So this is radius of deformation. This column is typical of the atmosphere. This column is typical of the ocean. The smaller radius of deformation. The Z or Z grid, I guess, for Dave, is the vorticity divergence one, and he showed that here's a typical how the continuous pattern should look. This is the X direction, the Y direction. Out here you're getting to 2 grid length waves in the X direction. Out here 2 grid length waves in the Y direction. And this is the how the frequency response should look for the continuous equations. So the Z grid is the same sort of shape, very similar to the C grid. This reversible arrangement I've got is also, again, extremely similar to the C or Z grid, but the B grid has got the wrong sort of shape, and the unstaggered A grid is too flat. The ocean's a bit different. Again, the Z grid is very good, or it's the right sort of shape. A grid's again too flat. The B grid's better than the C grid for the ocean, although it's still not exactly what you want out in this corner. This is the R grid, and because of the pivot point being 3/4 of the way along, it introduces an asymmetry. But if you move the pivot point from time to time to the other direction, it cancels out this asymmetry, it reverses. And so if you alternate your pivot points from time to time, and something like every 6 hours is probably fine, or I've played around a bit with it, doesn't make too much difference. But it does seem a good idea to reverse it from time to time. The VCAM, which I'll show later, I wasn't doing any reversing in recent times, and the solution was suffering, but once I reversed it from time to time, that's when everything...
Why would you not reverse it? Once every time step?
I was lazy. Once every time step. You can do every time step.
I said, no, less than that. Every time step, do you do both? So that
you go backwards and forwards in the one time step.
Yeah.
It's just every so often you might like to move the pivot point, so when you go backwards and forwards, it's flipping this asymmetry.
I mean, is it expensive to change it? Why
No.
do you do it more?
No expense at all. There's issues of whether you want to be, when you flip the sign, do you want to keep the unstaggered one as the truth going during the flipping, or the staggered one, staggered or unstaggered? In fact, you want to keep the staggered one because that's preserving the divergence. You don't.
So when you
don't want
flip
to mess
you
that up.
lose the properties of one of the grids.
The unstaggered one will
So when you
Will
flip it, it's
change
pure
a bit.
C grid.
it'll change a little bit. The velocities only will change a little bit. If it's a smooth field, then there's nothing there. It's only if there's some sharp gradients that you'll see an effect in this reverse and the flipping.
Could you just clarify where you're doing this interpolation in for the wave equation with C grid? You just everything's in the right place to difference. And so I'm not sure where you're doing this interpolation.
It's doing the gravity wave type calculation, so in the semi-implicit. I'll put some equations up in a minute and probably clearer there. So just showing what waves do in this reversible process. So a two-grid wave on the unstaggered system is also a two-grid wave on the staggered one. It's displaced a bit. Three-grid wave is just moved a little bit. Four-grid wave, and so on. Six-grid. These are some different number of points you can use, and whether you use the Van der Mon treatment or a simpler interpolation. The Van der Mon gives you this higher accuracy for no expense. So I can't read the captions to know which is which anymore, but they're all pretty good. Semi-Lagrangian method. There's a few non-NWP people here, so it might be worth mentioning just how that works. So if the temperature equation, you've got the advection, horizontal and vertical advection of temperature, you've got a adiabatic term related to the vertical velocity, and then you've got various physics and other nonlinear terms. So semi-Lagrangian, we average the equations along the trajectory. So we organise this as this is the new value, this is the upstream value. So we've got a t at the new value minus and the t at the old value. We should divide by delta t. And then the other terms we're averaging along the trajectory. So there's half of this term at the arrival point and half at the departure point. Often there's an off-centering needed. Near mountains you can get a resonance effect, and Andre Robert, I think, tracked this one down. That's a little bit optional. But the thing is, you get a reasonably linear system here in the new time values related to known quantities. So you end up with a coupled system of equations with a Helmholtz equation. There's various tricks you can do, and this is The reversible staggering, I won't go right through this, but you've got this pressure gradient term here in the Coriolis. This pressure gradient term, it's naturally located at the staggered position. You've got the temperature and pressure in the centre of the grid points, and during this calculation the winds are at the edges. So these are staggered winds we're looking at here. Maybe this is what Joe was getting at. So this is in the staggered U equation. So we have the pressure gradient calculated at the staggered U positions, but that's not naturally available there. It's naturally available.
It isn't P.
Oh, sorry, it is.
Grid point on each side of U, so.
Sorry, it is. P is at the right position, but in the we need to get this upstream value. So we need to evaluate this using the non-staggered values. It's the departure point calculations are all done in terms of non-staggered values, and this is a trick to let the pressure gradient work out consistent with what's coming later. But it's not so important for so I'll better move on from that unless you really want to. A more interesting one is surface pressure in mountains. Semi-Lagrangian models, you have an upstream value of the surface pressure and some divergence terms. Surface pressure is strongly affected by topography. If you've got a mountain, you're looking upstream over the mountain, and if you're doing a cubic interpolation to find this upstream value of surface pressure, you're getting some nasty overshooting effects because of the mountain's there. So there's a trick to do here to get rid of the mountains in this problem. So if we define an associated variable here, it's a bit like the log of surface MSL pressure. You can put in the contribution of the topography ZS with some reference temperature, and this quantity now varies quite smoothly even over terrain. So what we're after is an upstream value of this fellow, but the upstream value of log surface pressure is upstream value of this new variable and upstream value of this one. This one is a nice smoothly varying quantity. We can use bicubic interpolation quite happily on this one, but we don't want to use bicubic interpolation on this one because we'll get all sorts of overshooting from the mountains. So what we do is bilinear interpolation of this one, and that's essentially exact if we regard our topography as being the model topography as being a bilinear interpolation of these specified grid point values, then that term is handled exactly. So that works very nicely. I don't think anyone else has bothered doing that, but it's an easy thing to do. And similar with temperature. Temperature also has some nasty behaviour near orography. And again, we can set up a variable, this T hat, which is the temperature at a level, and we can add this topography contribution. So we have some reference temperature gradient, and this will cancel out most of the topography variation that is upsetting T. And this gamma, you can come up with a little expression how to define it in the vertical. So this, we've got an upstream value of the temperature, so it's an upstream value of this T hat, which now varies quite smoothly over topography, and this fellow which has just got this ZS. So again, bilinear for this term, and bicubic for this one, and you get rid of the most of your topography effects as regards to the interpolation needed for the semi-Lagrangian. And so it does seem to avoid the requirement for hybrid coordinates, but unfortunately that's not available in VCAM. VCAM I've had to use hybrid coordinates, but this one we don't need them. I should keep an eye on time at some stage. There's no posterior conservation. I think I'd better keep moving, or that's not so interesting. Helmholtz solver I don't really need to show, but I like my 3-colour picture. So if you do it with successive over-relaxation, instead of a red-black scheme, you have a red-blue-green scheme. And each of those is decoupled, so you could use a vector on the blue ones, then the red ones, then the green ones, and did that originally. Although these days, actually put in a conjugate gradient solver, which is nowhere near as colourful. I did also, in the early times, I did actually code up the conformal octagon grid too, which was one that Jim Purser devised, which has 14 panels. And that one, if you're interested, has a 4-colour scheme for the Helmholtz equation.
Are those two solver options mutually exclusive? Because a fairly standard thing to do with the SOR accelerators, conjugate gradient.
So is what exclusive?
Are those, so you said you're using SOR, but actually for real you normally use conjugate gradient. Well, a fairly standard solution for a Helmholtz problem would be to use SOR accelerated conjugate gradient. It sounds like you have all the bits sitting there to do SOR accelerated.
My colleague Martin Dix put in the conjugate gradient, so I don't know anything about that really, but okay.
Well, so you use the SOR as a precondition.
As a precondition.
I guess he probably does that.
Okay. Yeah, we still turn on the SOR from time to time. It works okay. Just in the highly stretched cases, it's one or other seems to work, converge a bit better.
So this is exactly the point where Stefan's point comes in. So when you actually refine your mesh, you should see with this method or with the CG that the iterations go up because of the poles. Yes,
there's extra. The over-relaxation factor needs to take that into account, and it's I don't remember how to get around it, but it's a bit tricky, yeah. So we've implemented MPI some time back, well Martin Dix did, and this is just showing one of the processes surrounded by 4 of the others, and so I've organised the variables as one long vector for each CPU, and then east, north, south, east and west regions needed for the message passing. So that means you've got the one long vector where you do all your physics and so on. You don't do the physics in this extended region. So a lot of indirect addressing. The overhead doesn't seem too bad, but well, it's not bad at all actually. But it does look a bit surprised. But it adds maybe it's 30% in these particular routines, but up to 30%.
In the I section, in the white section,
yep.
That vector, is that presumably in the interior? That's just a structured ordering.
Yeah, just from one end to the other.
Right, so then it's less surprising because you're indirect addressing, but you're not missing cache. So
okay,
that's.
Okay.
So you are using indirect addressing in the white area.
Yes.
But the major sin in indirect addressing tends to be the cache misses rather than the actual indirect addressing operation. So
that does make the code much simpler.
Sure.
It's just north, south, east, west values rather than I+1, I -1. So
yeah, it's not really indirect addressing which is the problem, is data locality.
Correct.
And if you use indirect addressing, you say, I don't care, I don't manage data locality anymore. So usually you don't, and you end up with really bad data locality. If you use arrays, you have data locality built in. So,
I guess early on I did use the non-indirect one, but it's you get a lot more, it's much harder to spot the bugs with that. Semi-Lagrangian, You do this departure point computation on demand, so it's a little bit of an overhead. Preferred number of processes, these sort of numbers, 1, 2, 3, 4, 6, 12, etc. Here's a recent MPI performance just a week ago. So this was on 50-kilometre global run. So it's C192, which is 192 by 192 on each of the 6 panels. So it's a fairly large computation. And did some timing runs. These are 1-month runs, full physics and everything, from 1 up to 288 processes. And so 200, that's the ideal blue line. 288 processes is running at about.
How much of your time is spent in the Helmut zone?
Nothing particular. I've got the figures. I'd have to look it up, but there's no particular region. Reversible interpolation takes a bit, but not too bad. So this is, you can either do face-centered or uniform decomposition. Face-centered means you try to have one processor per panel if you can manage it. Uniform decomposition is you have a processor and you give a bit to each of the 6 panels. So it seems a strange thing to do, but for load balancing it helps in some situations if you're doing the sunshine is spread over all the processes. I normally do this face-centered, but colleague Marcus likes, with an expensive radiation scheme, you get the better load balancing, but once you go above 64 processes, you're better to go back to the face-centered. VCAM is sitting down here. I've only run up to 6 processes, but the speed is much the same as CCAM. CCAM, we've got the allocatable memory, so it's easy to run with as many processors as you like, but haven't made the other one allocatable. Just an example of a name it run, observed rainfall and CCAM, DGF, JJA, so we run variable resolution, but I like to make sure it still works fine with the 200 kilometres. If you make some improvement somewhere else, you don't want to mess it up. So the Schmidt transformation here, I better hurry up or I won't get to VCAM. But this is, you move one of your panels over the region of interest, and then there's this zooming operation called a Schmidt transformation, and that preserves the orthogonality or conformality. So the original grid's orthogonal, and so is the one after the Schmidt transformation. So it's just the same equations, just different map factor.
We apply the Schmidt transformation first on sphere, then apply the cubic transformation, conformal cubic mesh. I see there are 2 things involved here. First, like already you have a conformal cubic.
I set up the mesh on the uniform grid, and then move it to where you want, and then do the zooming. So it's calculating the grid point locations after the zooming, and the map factors to do with that. Well, map factors can be got just by differentiation of the neighbouring points. But,
excuse me. What is the ratio between the smallest grids and the largest grids?
In the quasi-uniform one I showed earlier, I think it's about 3 to 1. But as you get more grid points, it does get a bit more crowded. This will still be 3 to 1. The distance, grid spacing here, and the finest one there will still be 3 to 1.
3 to 1.
I think out here also that will be one third of in that neighbouring panel. And this is the same number of grid points, zooming even more. So this is going down to 8 kilometres over New Zealand. That's what it looks like up close, so it looks quite reasonable here, but it looks a bit bit different here. We're a bit biased against the northern hemisphere. And there's the 1 kilometre version. We don't need the northern hemisphere so much over there. But we this is a side interest. We do some forecasting for Lingi and also in the Olympics we've supported our sailing team. So. And we've got 3 gold and 1 silver, so all due to CCAM. If you're running those stretch ones, then you can't really do a standalone one. You must run the bit courser and use that to assist the course region, which assists the course region of that one. That's the regional climate thing, but I'm running out for VCAM. But the way of assisting the broad scale region is that we use a digital filter, and we've got a paper, Marcus Satcher and myself, and it's like a 2D collocation or Fourier transform, and you want to, in a grid point, you want to know whether it's part of the fine scale field or the broad scale field, and the broad scale we define as roughly the width of that panel. So we want to know, is it broader length scales than that, or finer length scale. So each grid point's got a sum of a broad scale and a fine scale component. And then when we do the filtering later, we replace the broad scale part by the next model up, which is just handling that length scale properly. So periodically replace the broad scale fields by that higher one. But I haven't really got time to go into that. We've taken part in the Equiplanet one, but I haven't got time for that either. And we used the non-hydrostatic Miller-White equation, which is working again. And you actually get it for nothing. In CCAM, because you're doing a Helmholtz solver, the Miller-White term gets bundled in with the ordinary Helmholtz solver, and you approximate a few terms, but you essentially get it for nothing. And this is just using that, showing the cold bubble tests, using a highly stretched grid on the sphere down to about 500 metres, 35 levels. This is the non-hydrostatic one showing a cold bubble falling to the surface. And as it falls, as the omega, you get these vortices spreading outwards. This is after it falls. If you do the hydrostatic calculation, you get a falling bubble, but it's not such a nice shape, and the vertical velocity field is nowhere near as good. So that's just showing how that works. Well, I better get onto onto the non-conformal or the mnemonic grid, VCAM. So now we're back to what the other people do, equiangular grid. So looking at the grid points again, we avoid the crowding near the vertices, but we have contravariant and covariant wind components. So as far as divergence calculations go, we want these contravariant components, the ones that are normal to the edges. But luckily, if you follow these little directions around here, since they're normal to these grid lines, they actually vary nice and smoothly because these lines are all parallel to one another. So we can use our reversal interpolation to go from the contravariant components at the centre of the cells to the values on the edges. So that's a piece of good luck. That's not true for the covariant. Covariant components are the ones just joining those lines, and there is the direction change at the edge. But as far as fluxes in and out of the cells go, or divergence calculations go, it's these contravariant components we're after. And the reversible interpolation still works. So it's using the equiangular mnemonic grid. So it's very much more uniform. You don't have the crowding at the vertices, so few worries for parameterizations. I've already mentioned we used the reversible staggering again. Now it's the flux conserving form of the equations, which is better if you're doing trace gas studies. Using TVD or finite volume type methods for the advection. Gravity waves solving with a forward-backward solver, and so that avoids the Helmholtz solver. And semi-Lagrangian methods, you need to linearise some of the terms for the gravity wave equations. To get that Helmholtz equation, there's some reference temperatures you need to introduce, and we don't need to do that here because we're solving the full equation. So some people debate whether those terms are important, but they may well be. Just showing contravariant and covariant, etc. Here's a typical cell. So we've got the normal component is the contravariant U, that's the covariant, the contravariant V, and then you've got the ones along the grid lines. So if we call them tangential components instead, and normal components, usually I archive the contravariant U and the normal V. It's not strictly the covariant one. The covariant, there's an extra scaling in the calculation. But if keeping this normal to the edges and the one at right angles to it, so this fellow and this one, they're archived and they're orthogonal. So in the physics, you just use those two quite happily as if they're U and V. Wind speed is just calculated from those. So it just makes life a bit easier. The true covariant component, it's a linear combination of those UTs and VTs, and that satisfies this advection type equation. Those are covariant U's and V's in this advection equation, which is not needed much, but a little bit in the flux solver. So flux form of the equations, we have continuity. These high-speed terms we're calculating on the forward-backward part of the scheme with this small time step, delta T dash. Temperature and equation, we have these advective type terms, horizontal and vertical. That's done with a larger time step, but these high-speed terms, the adiabatic terms, they're included in the forward-backward delta T dash leg. Momentum equations, again, these are advective type timescale, horizontal, vertical, and then you've got the pressure gradient and type terms. And the Coriolis, I've got those in the small time step. I was hoping the Coriolis could be done with a larger time step, but seems not. I probably should have realised that in advance, but the Coriolis you need to have some geostrophic adjustment going on between the pressure gradient and the Coriolis terms. You can't leave this one till later. You get nasty oscillate, or it blows up if you try doing that. So this is normal velocities. I kept the map factors because that carries over to CCAM. Just felt lazy. If you calculate, most of it can be done in terms of map factors instead of more elegant methods. Now the advection was harder work than I was expecting. So in one dimension you've got the TVD type approaches, they're well developed, and you produce low order upwind fluxes and high order fluxes, and you use a flux limiter to combine them with some weight, which is called the flux limiter. Using mostly the super B limiter but the others are available. For 3 dimensions it's more complicated, and you need to include these transverse contributions, and I'm loosely following Randy Levesque's description of this, and it seems you need these transverse contributions. So this is describing it here. I've got some quantity Q at the centre which we're advecting. We want the low order flux at the boundary is the upstream value of Q multiplied by this edge value of U. Same for V, same on the other faces. The higher order terms, you want an edge value a higher order edge value multiplied by this, and it's usual to use something like a Lax-Wendroff treatment to get an upstream effect there, and that needs some covariant velocity, so that's a slight nuisance. And there's choices of that edge value. Is it a linear interpolation, or should one try using something a bit higher order? I should mention these velocities here, these reversible ones. I was making a point of that somewhere earlier. I must have forgotten. No, it must be coming up. Okay. Advecting the velocity components, if your Q is replaced by the winds, then it's easiest to just replace it by the three Cartesian components, U, V and W. That way you don't have to worry about the twisting effects of is U being rotated to a V as you go from one panel to the next. So just they behaved quite nicely. The transverse components. This low order is not just the centre value here. It has to take account of the advection in the transverse direction. And so what I'm doing here is I'm producing an intermediate QX and QY at the centre, taking account of this advection in the covariant velocities, and then using those as in the edge values. Maybe people can tell me an improved way to do that, but we have the covariant velocities at the centre of the cell. We don't actually have them at the edges, and at the panel boundaries the covariant ones can change directions. So it's simpler to just use the centre ones if you can, rather than try averaging them or do some upstream calculation of which covariant one you use. Is it from this cell or from that cell, depending on, you can do that as well. So the solution procedure. Well, this is just in the forward-backward part, we calculate the divergence using those staggered velocities and integrate those to give the vertical velocities. Time splitting, I might just go on to here. So this is showing the solution procedure. So we have a main time loop, and now we have this small sub-step forward-backward loop. So we need to stagger the U and V to these staggered positions. We need to get some averaged surface pressures, and then we calculate the divergence, sigma dots, omegas at each of the grid points. We update the surface pressure using the integrated divergence. Calculate phi, and we calculate the pressure gradient terms, the staggered ones, and they need to be unstaggered to calculate the Coriolis. They're unstaggered as well as the U and V, and that's when the Coriolis is done. Then we go back and we have to do this staggering again. And then the advection is done here. But we need to be a bit careful using the U's and V's. They need to be consistent with what was used for the updating the continuity equation, the surface pressure. You need to make sure that the it's actually the average of these sub-time values of U and V that get used here to make sure that they're self-consistent. So the continuity equation is consistent. If you advect the quantity 1, you want to make sure it still gives 1, and that's equivalent to having this continuity equation. So the main MPI overhead is this reversible staggering at each sub-step. It's not too bad, and you also because it just needs the nearest neighbours, so it's just one bounds call each time. Message passing is also needed for the pressure gradient and divergence calculations. This is an example of an advection, just cylinder here, letting it go around the world in 900 steps. I think I can probably do it more accurately than that, but it doesn't look as accurate as I can get, but it's not too bad. Before I brought in hybrid coordinates, looking at the monthly average of vertical velocities, you could see these patterns, especially near the Andes. There was these plus and minuses which are spurious. Introducing hybrid coordinates in the vertical gets rid of that. Oh, sorry, there's the hybrid ones up here, so it gets rid of those problems. There was a bit of a problem in Asia as well. That didn't occur in CCAM. This is the same CCAM over Asia and over South America, North America, so there was no need for hybrid coordinates here. That you weren't getting those effects. And this is just showing the rainfall similar between those two. Getting close to the end. The VCAM, no Helmholtz equation needed. There's no linearisation needed in the gravity wave calculation. Mass and moisture conserving. It's more modular and probably simpler. You don't have to worry about semi-Lagrangian resonances. MPI is simpler in principle. The semi-Lagrangian needs this computation on demand, which can be an overhead. Disadvantages: Courant number of 1, so you need to reduce the time step if the jet streams get too strong. Some overheads from the reversible staggering, and the non-hydrostatic treatment I don't think I can use Miller-White easily, or with no benefit using Miller-White in this one because there's no Helmholtz equation already being done. Now, when I was looking a few weeks ago, the jet stream seemed weaker in VCAM, but last night I plotted them again, and they're all under control. So this is the 4 seasons, just the jet stream VCAM here. So it's maybe even a little bit stronger than CCAM. So that's under control. And then just a 1-year run with exactly the same physics. This is the observed climate, DJF, JJA. VCAM is actually looking better over this South Pacific convergence zone and the Indonesian region. This colours the rainfall, high rainfall here, DJF. Indian monsoons is quite reasonable too, and so the pattern's quite good, and it's actually looking better than CCAM in those regions, which didn't seem to be the case a week ago. So.
How much difference is the time step in between the VCAM and CCAM?
Using a little bit smaller time step here, this is 200 kilometre runs. I think one of them is 30 minutes time step and the other is 40, something like that.
Okay, so even with the semi-implicit one, semi-Lagrangian one, you're not significantly violating the CFL?
No, I'm not pushing it hard. Just it just lets you relax near the vertices. You don't have to worry. Near the vertex, the Courant number will be over 1, but the physics, you don't want the time step too large. So that was a pleasant surprise yesterday. But I think previously I hadn't been alternating the reversing, and you can build up a little bit of a bias, especially in tropical regions, I think. So there's better rain over SPZ in Indonesia, and that's what I was hoping for, because this linearisation, the the PS term, the pressure gradients, and the slowing down of the gravity waves in semi-implicit, you'd think may affect those tropical regions. So that's all looking promising now, and so it seems to work well for both models, so I'll stop there.
If you're running about the same time step, why would you be slowing down the gravity waves in the CCAM version?
CCAM is doing a 30-minute time step, but the gravity waves are handled by the sub-time steps, which is about 8.
Oh, right.
Doing about 8 sub-time steps for each full one, so that's 3 minutes or 3 or 4 minutes.
John, so you're in VCAM, your sub-stepping is replacing, that's how you get around this Helmholtz problem?
Yes.
Okay, so I guess in terms of difficulty, is there any difficulty in adding the Helmholtz problem to VCAM? What's the issue with that? It doesn't seem like it's a value very much, but...
Well, for the non-hydrostatic type calculation, I haven't thought about it yet, but other people have done that.
Because it's not orthogonal, so your character is more complex to them. Because you have the initial terms.
I don't expect any particular problem, but I imagine other people have already done that with their mnemonic grids.
How do they compare performance?
Oh, very similar. That was that speed thing. I've only gone up to 6 processes with this one, because I thought I had some fundamental problem to solve, but the fundamental problem's gone away, I think. Oh, it's not completely gone away, I should say. My main reservation here is my rainfall over China is this green colour. Really want the yellow colour because we do a lot of runs over this region. So there's something not quite right. Also the rainfall over the Amazon is a bit light on, but that's true in both runs.
Are the error patterns related to the corner? Are the errors correlated with the geometric corner of the grid?
No. The corner of the grid's somewhere up here, or near Japan, so that's a bit far from China. There's another corner just below Australia there.
So, what's the resolution? Sorry, I missed it.
Oh, this is about 200 kilometres. 200. Not pushing it too hard there.
Do you think you could extend the reversible staggering ideas to a non-line or non-structured meshes? I would be quite keen to try and quite crazy.
Don't know.
You would get a linear system, which you would still get a linear system for interpolation, so you could also invert that.
We need to define a line going
you would need to define the interpolation in 2 dimensions rather than 1, but is the principle extend? I guess you couldn't really, because the dispersion analysis in 1D, I guess.
The line doesn't need to be a straight line, but it needs to be contiguous or joined up somehow and have some meaning.
It might be expensive, but a 2D interpolation, an invertible, two-dimensional interpolation.
Yeah, it should lead to a sparse matrix.
It looks, so I was thinking about this during the talk, this one-dimensional reversible interpolation kind of looks like a Galerkin projection with a particular choice of projection. So I'm wondering if that's what's going on here. And you certainly end up with a system with the same structure that you would expect. And so it might be approaching that.
I was holding back with my question. I blinked when you described the reversion, and so I completely missed. I was struggling after. Because it reminds me of the. So you're going to the divergence vorticity in the middle or not? Are you going between pressure, velocity to vorticity divergence and then back to on the staggered one?
Just the wind components.
Yeah, but you have to compute. So you have to compute divergence vorticity in order to get the pressure velocity at the other points, or not?
Not sure about pressure velocity.
No, okay. No, because it reminded me of the control variable transform in data simulation, where basically you go between these vorticity stream function. Divergence.
But the trick here is that there were two choices. You could have biased it in one direction.
Okay.
And you made a point that you kind of have a cancellation of errors if you change the bias from terms of which is actually something I hadn't thought of. But that was one reason I have never bought into it before, because you have to have a bias at any particular time.
When I saw the paper, it was Nigel Wood actually pointed that out. That what to do about this bias, and if you do the same analysis but alternated, it does cancel out. It's just a bit of choice how often you want to do it. Because it does give it a little bit of a kick when you reverse the direction, at least a kick to the physics. Okay. Thank you.